I think it's great.
You like it, Vanessa? Yeah, Vanessa's obviously got a good sense of humour. Get it? Knick-knack, paddywhack, give the frog a loan.
Yeah. Sounds like
Nick.
you've been watching Dave Allen.
Well, I was a student, so I don't know where or what that person was watching. So let's get started, everyone. We are beginning a new section today. We are expanding. Every day that we do this right now, we are expanding how to differentiate things. The chain rule tends to be one of the hardest ones for people to get their heads around. And I think the reason for it is that there isn't really a formula. I know it's going to be written as a formula, and I'm going to show you that formula, but in practice, it's more of a process and less of a formula. So for completeness sake, let's show you some of the guys we do know. This is called the product rule, right? If you want to differentiate this guy, the derivative is f dash g plus f of g dash. Isn't that kind of plug and chuck, right? You know who f is, you know who g, you plug in, you make it look pretty. And that's called the product rule. And we've had a lot of practice in that. We have a thing called the quotient rule. Basically, if your function that you're trying to differentiate is a fraction, quotient is the old name for a fraction, then it's f dash g, take away f of g dashed over g squared, right? We've done that. Right? We have a power rule, right? Add, multiply by the power, right? And then reduce the power by 1. Think we have just good memory. Just remember that the derivative of sine is cosine. Oh, here's a little test for you. What's the derivative of secant x? We did 6 trig functions and their derivatives. What is the derivative of secant x?
Secant x tan of x.
Good. Be honest. Did you know that or did you look it up?
I knew it, but mostly because I was doing the homework yesterday and
it's so fresh in your mind. Right. You know, it's just helpful if you can memorize these things, because if you have to look up everything, isn't it going to slow down your thought process? Because you find something, then you write it down. And for me personally, if I interrupt my thought process, I tend to make more mistakes or forget where in the process I am. Those guys we know. So what the chain rule does is it allows us to integrate what is in 141 jargon, a composition of functions. So y is equal to f of g of x. Can you remember Fogs and Goths from 141? What the chain rule does is it allows us to differentiate this. And I did say it's a formula, but we don't really use it as a formula, mostly because it isn't that helpful. So if y is a function of g of x, then the derivative is f dashed of g of x times g dashed of x. And that is called the chain rule. Now, what the chain rule does is it expands the number of things you can differentiate, like by 1,000,000%. You can only multiply and divide product and quotient rule when the pieces are relatively simple, right? You can only differentiate x squared e to the x, right? Things like that. You can only differentiate sine x over x squared plus 1. They're quite primitive, right? They're good for what they do, but they're quite primitive. What the chain rule does is it basically allows us to do almost anything within reason that is doable. So I'm going to show you an example of why the chain rule had to be found. Can you imagine there was a time where differentiation was just beginning, right? People had just understood it. They were looking into how to find derivatives. And somebody came up and said, hey guys, how are we going to do this? Now, the processes that we know right now are not very practical. couldn't I just FOIL that thing out and then differentiate using the power rule? Does anybody here want to FOIL that thing out? Nobody in their right mind. You couldn't pay me enough money to FOIL that out. Wouldn't it take me days, and I'd probably screw it up somewhere. I could call it 3x squared plus 1 times 3x squared plus 1. And couldn't I do a really horrendous version of the product rule? I know we do a product rule with 2, and if at a push, can't we do it with 3 terms, right? Can you imagine that if you did it with 100 terms, it would be a forget it, right? I guess the third alternative is, okay, let's just not bother, right? Just ignore the question. But that didn't work. So what they figured out was this trick called the chain rule. So you're going to find these terms used in some textbooks. There's a guy called the inside function, and there's another guy going to be called the outside function. So let me rewrite this guy down. The inside function is 3x squared plus 1. The outside function if I cover this inside the brackets with my finger, right? One finger's probably enough, right? That guy there. This function is basically something to the power 100. So the outside function is something to the power 100. And this is how you differentiate them. I tend to use a little bit different than inside, outside, but in other videos and textbooks, we'll use that. So I want you to get used to the terms. I just call this something to the power 100. Now, if you want to differentiate something to the power 100, it's 100 somethings to the power of 99. Would you agree that is the rule called the power rule? Something to the power 100, 100 somethings to 99. And then you finish with the derivative of the inside function, the derivative of this, and that is 6x. And then you make it pretty. You get 600x, 3x squared plus 1 to the power of 99. Wasn't that really cool and really quick? That is the chain rule. It's essentially this formula, but do you see it doesn't really work? You can't really talk about this function. There's no advantage to using it. It's there, but you don't use it. I think of this as a process, right? 100, well, in this case, something to the power 100, 100 somethings to 99 times the derivative of the something. Yeah. Practice makes perfect. The more of these guys I do, the better it gets. And that's what I'm hoping for you lot as well. So how about y equals sin x plus 1 to the power of 10. Now you want to do the chain rule on that. It's derivative. Something to the power of 10. 10 times something to the power of 9. Isn't that general? And you finish with the derivative of something, the derivative of the inside function. What is the derivative of sin x plus 1?
Cosine x.
Correct. And you want to make things pretty. 10 times cosine times sin x plus 1. Now, if you look at the original question, I'm amazed even today at how elegant that solution is. Isn't it relatively quick to do? I mean, they'll get harder, but right now it's relatively quick. Yeah. Let's put in a square root. And inside that square root, I'm going to have 3 sin x plus 2e to the x. So I'm going to make that really ugly, all right? If I want to do the chain rule, I need to turn this into a half power, okay? If somebody said, find the derivative of the square root of x, wouldn't I call it x to the half, right? Same reason. Now, in this format here, the thing in the brackets is the something. So what am I looking at? Something to the half. So you want to differentiate something to the half. It's 1/2 something. Reduce the power by 1. And then you finish with the derivative of the inside function, the something. Differentiate 3 sine, you get 3 cosine. Differentiate this guy, you get 2e to the x. That's it. We're finished with the derivative. What we're going to do now is make it look pretty, right? Style points. Now, I don't care what that looks like. It's still to the -1/2. So I'm going to have 3 cosine x's plus 2e to the x. That 2 belongs downstairs. And this guy is now going to be that guy. Are we good with that piece of algebra? Negative powers become fractions with positives powers. There's one more thing to make this pretty. And that is make it look like the original. So how should I rewrite the bottom so that it looks like the original?
Square root of 3 sine x plus 2e to the x.
Agreed. Now just look at how ugly that function is, yet within 4 lines we got its derivative. And you notice I'm not using that formula, right? Isn't it a process? Something to the power of half, something to the power of 10. Now, they don't always need to be somethings to the powers. Here's one where the chain rule works. E to the power of sine x. Now, if you want to do the chain rule on that, it's e to the something. So if you differentiate e to the something, you get e to the something times. And in the chain rule, don't you then differentiate by the something? So the inside function, as it's called, sine x. And if you differentiate that, you get cosine x. So the derivative of e to the power of sine x is cosine x times e to the sine x. I'll take a volunteer for this one then. E to the power of 10x squared, right? E to the power of something. Chain rule, differentiate. Okay, thought someone was about to speak there. E to the something.
E to the 10x squared times 20x.
Nailed it. Maybe we're just shy. That's what it is. We're shy. Well done. You got it. What other kind of functions should we do? I'm trying to just pick on my own before I start looking at theirs. Yeah. Okay, how about this one? This is a version of question 1. So they have a function, and it's 2x cubed take away ax squared plus 9 to the power of 5. And we are going to find its derivative using the chain rule. What is the inside function here? That's a guy I call something. What is the inside function here?
Polynomial 2x.
all that stuff. Agreed? So 5 times something to the power of 4 times the derivative of the inside function, which is what? Derivative of that is 6x squared, take away 16x. And we now have 5 lots of 6x squared, take away 16x, and finish with 2x cubed, take away 8x squared, plus 9 to the power of 4. So the style points. Oh, I was too quick for my own good here. There are 3 rules to style points. Rule number 1, make it look like the original, which it does. Rule number 2, factor the heck out of it. And rule number 3, if there's any trig identities around, try and find them and use them. Can you see that I can factor out something that I haven't yet? I think I caught it. What did you say? What can you factor out?
X out of the first one.
Yeah, and the second. What about a number?
2.
So how about taking out a 2x, and that'll leave me with a 3x, take away 8. Now, style points are important because we want everybody to write the answer the same way, so it's easier to check. Secondly, if things are written in this format, can't you find the places where the derivative is 0 relatively easy? Would you agree that x equals 0, the derivative is going to be 0, and that x equals a rather ugly 8/3? So I know that this original curve has a hill or a valley at x equals 0, and another hill or valley at x equals 3. So it gives me interesting places which are actually got a name called critical numbers. Now let's jump to a really ugly one, and this is version 3. It's 1 over a cube root. Yeah. Oh, that is ugly looking. Agreed? Before I even attempt to do the chain rule, because I know that is going to be a chain rule question, don't I have to rewrite this as a fractional power so I can use the big version of the power rule on it, right? So it's going to be this guy, that's our inside function. What power is 1 over the cube root going to become if I write it this way? 1 over a cube root.
-1/3.
Agreed. Now I can do the chain rule, right? Something to the power of -3. So the power rule is you multiply by the power and you reduce the power by 1. But in the chain rule, don't you also finish with the derivative of the inside function? In this case, the derivative of that is 4x. And then you start doing style points. This is -4/3 x. Too late. I did this line. I probably don't need it. Right. I probably should have started with this line here. There's going to be a -4x here and a 3 lots of that guy. Are you happy about the negative fractional power becoming this guy? The -4x in the top and the 3 in the bottom. And to finish with, make it look like the original. And anything to the power of 4/3 is a cube root. And the 4 tells me that the thing is raised to the power of 4. So that ugly fraction is the derivative of this cell in its perfect style point format. It's almost unlimited what you can differentiate now when you think of it as a function of a function, right? An inside and an outside function. So there's a pretty ugly looking fraction, definitely not as bad as this one. But if I want to do the chain rule on it, don't I have to call it that? Right? Fractional power becomes negative power. Now, when you differentiate, multiply by the power and reduce the power by 1. And then you differentiate what is the inside function, in this case, times 5. And so you get negative 60 when you combine the numbers. And this guy comes downstairs. Are we comfortable with that? Any questions so far? Let me throw a new function into the mix. Algebra is a skill that you really need to get good at, because in Calc 1, there's a lot of things that involve algebra just to get it into a format that allows us to differentiate, or at the end to do style points to get the answer the way it's meant to be written. And this function here is some weird fraction all raised to the power of 3. That is not a very good way to write it if you wanted to differentiate it. Now you could say, well, can't I just call this the something and go power rule? Well, you could, but then wouldn't you have to differentiate this ugly fraction? And you'll just have to trust me on this. The style points, if you went that road, would be horrendously ugly, right? You'd have some weird fraction with some other fractions next to it, and you wouldn't really be able to put them together. So I'm going to use a piece of algebra that says, if you have a fraction raised to any power, you can separate it like this. But 1 to the power of 3 is just 1. Now, what's that guy going to be? How am I going to rewrite this fraction power so that I can do the power rule and chain rule on it? How's that going to work out?
Is it 4t plus 1 to the negative third?
You nailed it. That's exactly what it is. Right, that's not the first time we've seen this, right? Now, experience helps, right? By the time you've seen 10 like this, you won't give it a second thought. You'll just do it because you know that's what you need to do to make this work. Now, in this particular question, then, it's going to be, right, something to the power of negative 3, multiply by the power, and reduce the power by 1. And you always finish with the derivative of the inside function. In this case, the derivative just gets you 4. You then make it look pretty. Style points. We comfortable with this guy? Let's put some trig in. This is a version of 6. The guy I call something, his other name is the inside function. What is the inside function in this question?
Theta cubed.
Yeah, the theta cubed, right? So cosine is something. If you differentiate a cosine, you will get the negative sign of that something. And then you finish by differentiating the something. You differentiate the inside function. And the convention is signs, numbers, powers, trig. So all I'm doing is rearranging the order. That wasn't too bad. Oh, here's one to give you a headache. The sine of cosine x. I have no idea what that looks like, but I bet you it's weird. We can differentiate this. Won't the inside function be cosine x? Right? The inside function will be cosine x. So this is basically the sine of something, right? That's how I think of it. The sine of something. So if you differentiate the sine of something, you get the cosine of something times the derivative of the inside function. So you get minus sine x. And so we go negative sine x, the cosine of cosine x. Now the cosine of cosine x is not cos squared x. Cosine x times cosine x is cos squared x. Isn't this a weird function? It's a cosine of the cosine of x, right? That's a weird function, but there's its derivative.
What's the, it says cosine, and then what does it say in between cosine and cosine x?
That there, it's just a very badly drawn bracket. So it says cos of cosine x. Do another trick one. Let's suppose y is tan to the power of 5 theta. If you want to differentiate this, it's probably a good idea to think it like that. Can you see the something? The inside function is tan theta. Is it clearer now? The inside function. So this is basic, isn't it? Just another power rule. Multiply by the power and reduce it by 1. Finish with, okay, what is the derivative of tan theta?
Secant squared theta?
Well done. Now, to make this pretty, 5 secant squared theta tan to the 4 theta. Do you see that we end up writing it like that? It's just cosmetic, but you know. I believe, just to prove me wrong here, that is the correct answer. But when you do it, if that was a question, and you're going to type it in to WebAssign, don't you have to do 5 bracket secant theta 2 bracket tan theta bracket 4? Don't you have to write it that way? Because WebAssign doesn't understand that. Right? We as humans do understand that, but that's a software issue. This is the correct answer, but that's how you have to write it in WebAssign. Have any of you had problems in WebAssign where you tried to do sine squared and it didn't like it, and you had to write it as brackets and put a square outside? Same reason, right? So this is the right answer, but that's what you need to type in to WebAssign to keep it happy. Rachel.
So yeah, so you wouldn't try to change the secant squared theta into tangent squared theta plus 1 and then try to combine them or anything?
You could, and mathematically it would be correct, but I think WebAssign isn't that clever. It's not as clever as we are, and you could probably do it and it would say you're wrong, because I suspect it's only got one answer in its little, this is the answer, check it. Oh, it's not what I wanted, it must be wrong. Trig is especially good at doing that. Isn't there like lots of different ways you can manipulate something in Trig? And although they look really good, and technically they probably would be correct, you wouldn't get anything because WebAssign won't understand it. So
Okay.
there are some things that you would expect WebAssign to understand, right? If I saw a sine squared plus a cos squared, right, that's turning into 1, agreed? Right, if I seen that, I would do it, but I wouldn't expect it to be able to handle too much more. Okay, one more of this type, and then I'm going to start mixing and matching, which just adds to the fun. It's not meant to be a trick question. Would you agree the inside function is x to the 4 take away 2x? The guy I called the something. So isn't this e to the something, essentially? So if you want its derivative, it's e to the something times the derivative of this. And if I'm being very lawyer-esque about it, couldn't I pull out a common factor of 2 while we're at it? Okay, nothing too shocking about that. Be comfortable. E to the something gets you e to the something times the derivative of that something, the derivative of the inside.
Was there a reason that it changed from x to the 4th to x squared?
Not now, because I wrote it down wrong. So it's meant to be x to the squared all the way through. So what we're going to do, we are going to take the chain rule and we're going to mix it and match it with a product rule or a quotient rule. What that allows us to do is to expand the things that we can differentiate even more. So let's show you an example of that happening. Suppose I wanted to differentiate that weird function, x cubed sine of x squared. It's actually got two distinct things going on. Would you agree that it's a product rule? Would you agree that this piece of the product rule, the sine of x squared, won't you have to use the chain rule on it to get its derivative? So isn't this got two processes, a product rule with some chain rule stuff in it? Now, what I tend to do when questions get really ugly like this is, in this case, it's going to be a product rule. So it's going to be f dash g plus f of g dashed. I go over here in the side and I say, that is f and its derivative is 3x squared. This is g. And I find its derivative here. And then I can just plug all the pieces in over here and it's done. Okay. Sine of x squared is a chain rule. The inside function is called x squared. So this is essentially sine of something. If you differentiate the sine of something, you get the cosine of something. Times what? What's missing? So derivative of sine x squared is the cosine of x squared times something. What's missing?
2x.
Great. Now I've got all these pieces, can't I just plug and chug it in here? So what's y dash going to be? It's going to be f dashed, which is this fella, 3x squared times, leave that guy alone, so it's the sine of x squared, plus leave this guy alone, and g dashed, which is the cosine of x squared times a 2x. And I now have 3x squared, the sine of x squared. Combine these and you get 2x to the 4 cosine x squared. Some style points. It looks like the original, so we can check that off our list. Can we factor the heck out of it? Even a little bit is better than nothing. Can anybody see a common factor?
X squared.
That's the one you use. And so you're going to have this fella plus this fella. And you give up. That's as good as it's going to be. You're finished. Are we good? Any questions? Try another one. Let's do y equals e to the sine x times, I don't know, cosine x. That'll be interesting. It's another product rule. F is going to be e to the power sine x. And g is just going to be cosine x. Derivative of e to the sine x is a chain rule, right? Differentiate e to the something, you get e to the something, times the derivative of sine x, which is cosine x. If you want to differentiate a cosine, it's negative sine x. So, right, there's the building blocks that are going to fit here. F dashed, which is all of this, put the cosine at the front because it looks nicer there, times g, which is just another cosine, plus f, which is this guy, times negative sine x. Style points. Is there anything that we can pull out as a common factor in this kind of ugly expression? This guy plus this guy. Is there anything that is a common factor?
E sine x.
Great. Now, while I'm at it, can't I do two cosines multiply to give me a cos squared x? And won't I get a takeaway sine x? And those two might be, but not in this case, be a trig identity. Would you agree that that doesn't look like it's a trig identity? Right. Can you pretend in a different question it had been, and this is a totally different question, but it had been this guy? Does anybody recognize what that fella can be rewritten as? It's a double angle from trig from 142. Cos squared takeaway sine squared. What in heck is that? Double angle.
Cosine 2x.
You nailed it. There you go. So if that had happened, wouldn't I take this and call it cosine 2x? Because remember our three rules. Make it look like the original, factor the heck out of it, and if it's trig, see if you can make it look pretty using an identity. In this case, can't do anything, so I'm finished. How are we doing, guys? Are we getting a little bit of feel for this chain rule as a process? It's not really a direct formula. Trying to get some blank papers. Wow, we've done a lot of questions today. So I'm going to give you a really ugly one on your own using a quotient rule, which I haven't shown you. Tomorrow we'll do a lot more, and we'll do certainly some quotient rules. So I want I need something here that makes that more interesting. There we go. Sine of x squared over the cosine of x squared plus x squared. You have got 3 minutes. Differentiate that using the chain rule and the quotient rule and make it look pretty. For those who need to kind of start. Okay, that's all I'm doing. Okay, last few things. Here goes. Top guy is the sine of x squared. If you differentiate a sine of something, you get the cosine of that something, and then you finish with times 2x. If you differentiate this fella, you will get negative the sine of something times 2x plus the derivative of x squared, which is 2x. So f dashed is 2x cosine of x squared times cosine of x squared plus x squared. Take away f, which is sine of x squared, and the derivative is this guy here. So that is negative 2, should say negative 2x. We're running short of room here. Sine x squared plus a 2x. And the bottom is just this guy squared. So that guy squared I'm not going to do. What have we got here? This guy times this guy gets you 2x cosine squared x squared plus 2x cubed cosine of x squared. If you multiply this guy and this guy together, you get plus 2x sine squared x squared. And this guy times that guy, I believe, gets you negative x sine of x squared all over that ugly guy squared. And if you take this guy and this guy, what do you get? It's the only two that really play. 2x cos squared plus 2x sine squared. Let's just focus on these two guys. If I pull out 2x as a common factor, I get this fella. What do you think that is equal to? Isn't sine squared theta plus cos squared theta 1? Isn't sine squared t plus cos squared t 1? Isn't sine squared x plus cos squared x 1? Do you know it doesn't matter what it is as long as it's the same what it is? Aren't these both x squared, but they still count? So that's 1. So 2x times 1 gets you 2x. So what you have is a 2x cubed cosine of x squared, and take away an x, sine of x squared, all over that ugly guy squared. And before we forget, put your name down and don't disappear quite yet. A week today, you are getting your midterm. When you turn up on your midterm, there's a 2-hour window. You can turn up at 11 and finish at 1. You can turn up at 12 and finish at 2. So if those time slots don't work for you, tell me about it, right? So you're 11 till 1 or 12 till 2, and that's going to be your midterm a week on Monday. Your midterm is going to be for the most part in Canvas as a PDF. So you'll actually be writing your working down. You're going to need to get familiar with a program called Microsoft Lens, which allows you to take pictures of your working, and then you're going to upload it into Canvas. If you go to Canvas, I've got videos showing you how to do it. The bottom line is you need to get a video. The midterm is a major exam. I have to make sure that everyone's treated fairly, and that means I can't do it unless I see that you're on your own and don't have your big sister beside you helping you with your work, right? So you've got a week, not that I haven't mentioned it in the syllabus and all sorts of places. So you've got a week to get a hold of, borrow a webcam so that I can do that. Your phone can count as a webcam, you know, you can do it that way and I can see you, but I need to see you, right? And so make sure that that's the case. Don't turn up on Monday and tell me you can't do something, because I can't make you do the test. It's not fair. I don't want to get into that game of I don't trust Rena because she's really devious looking, but Nick's so honest, he can tell me anything and I'll believe it. I'm not playing that game. So if you don't have a video, I can't give you, you're not doing the midterm. It's not fair. So you don't want to miss the midterm. If the time slots I gave you, to remind you, 11 till 1 or 12 to 2, if they don't work for you, you need to contact me and we'll figure out another time slot for the same day that will work for you. And I'll talk more about the details on over the coming week. Rachel.
Is it going to be open book, open note?
Yep.